How far back can we go to find a documented case of cancer in humans?
I mean, honestly, it probably goes back to the beginning of humanity. We find it in ancient Egypt and all these things. There's talk, so 2,000 plus years ago, we found cases of cancer. Now you have to understand that cancer, like a lot of diseases, is worse as you get older. So, as you go back further into prehistory, as the sort of people live only like 40 years or something like that, life expectancy in the 2000 years ago, you're going to get a lot less cancer than you do these days. But on the other hand, there were numerous mentions of it, even in the most early papyruses that we could find. They talked about cancer, which is super interesting. So it's a disease that has been here for a long, long time.
And as we converse here, it's going to make a lot more sense that the history does go back so far. But where I want to take things next is talk about modern times and our early understanding of cancer in the 1900s and beyond. So in your book, you talk about cancer paradigm 1. When does this take place? And then what are our early thoughts when it comes to cancer and what it is and how it works?
Right. So cancer, I mean, there was sort of always this idea that cancer is a disease of sort of excessive growth. So, this is in the modern era, right? Back in the 1400s, people talked about humors and stuff, but that wasn't very scientific. So in the modern era, the sort of initial thing was that, hey, this is something that's just growing too much. And this was obvious to see, of course. You'd see a lump and then it would grow and grow and you'd see it spread. So then people were like, well, if it grows, then let's find ways to kill it. And that's the sort of first paradigm of cancer that we had. The most ancient techniques, of course, were surgical. So you just cut it out. And they did that for a long time. But it's relatively unsuccessful as it is today just to cut it out, because the whole point is that it spreads. And it's not the actual size of the tumor that kills you, it's the spread of the tumor that kills you. And as we got into the modern era, then we started to see better ways of killing cells. It's the same paradigm, but more sophisticated ways to kill cells. So instead of just being able to cut it out, then they discovered X-rays. And, X-rays were discovered in the early 1900s. And within a couple of years, people were blasting X-rays at breast cancer, for example. So it was very interesting. It was the first case, or one of the first documented cases anyway, was of this medical student who decided that, hey, he was going to just point this X-ray machine at the breast cancer that somebody had, and then luckily there was like a tea, a thing of tea. So he took the foil from the tea and protected the skin around it, right? And that's sort of the first X-ray therapy. So you can burn it with radiation. But that's just another way of killing cells, same as surgery. And then in the World War I, they used the mustard gases as chemical weapons. But what they had noticed with that is that it kills certain cells faster than other cells. So again, as people started to develop that, they started to develop a chemotherapy. So what you had was a paradigm, and the paradigm means the way you look at cancer, what it is. So you're still looking at it as a problem of cell growth. So therefore, a solution is killing. So you can cut it out, surgery, you can burn it with radiation, or you can poison it with chemotherapy. And, it's not trivial. It's still sort of the basis of most of cancer medicine today. The problem, of course, is that there's a ton of side effects because you're killing cells. So every single one of these treatments is highly toxic to the body. And that's why you see, obviously with radiation and surgery, you can see it, but with chemotherapy, people's hair falls out, they get terrible nausea because you're killing off the lining of the intestines and stuff. But that was sort of the first paradigm of cancer, and still a very successful number of treatments developed from that. So yeah, that's where that came from.
We're going to pivot into paradigm 2 and talk about the, additional understanding that they that scientists gained over time. But when it comes to paradigm one, and basically all we know about cancer is there's these growths that are happening in the early days of modern times, what did they think was causing that?
They really didn't have any good idea of what was causing that. I mean, that was why we never sort of progressed. That paradigm had to shift because that was the whole thing, right? It's like they had no idea. Like you could see that this breast cancer or this colon cancer or lung cancer was getting bigger and bigger and bigger, but they didn't know why. So that led us to sort of the second great paradigm shift, which was the genetic paradigm. So you went from a growth paradigm, cell growth, to genetic paradigm. And it's not that one is wrong and one is right. They're both right. It's that the second paradigm takes your level of understanding sort of that extra level deeper. That is, instead of just saying, hey, stuff is growing, let's kill it. Again, and I'm not trying to trivialize it because it was very successful. Actually, chemotherapy and stuff did cure a lot of people. But what you're trying to do is take that to the next level and say, okay, I see that things are growing. Why are they growing? So it's not that paradigm one was wrong. It's just that paradigm two, which supplants it, is an attempt to explain what is happening here. And that's the genetic paradigm. So by the 50s and 60s, as they're starting to understand about genes and chromosomes and all this sort of stuff, people started to hypothesize that, hey, we have genes that control growth, or there should be genes that control growth. At the time, they actually hadn't discovered them. Maybe the problem with cancer is that you have damage to the gene, and as you damage that gene, it starts to grow. Or you have genes, for example, that are supposed to slow down growth. And as you damage that gene, it's going to allow growth to accelerate. And by the late 70s, they in fact discovered these exact genes. So they're called oncogenes and tumor suppressor genes. So oncogenes are actually, even though it sounds like a cancer gene, it's actually a growth gene. It's a normal growth gene. When you get a mutation in the oncogene, then you get excessive expression of this growth and therefore increased growth. Tumor suppression genes, again, I love these names, but they're actually normal genes. They don't cause tumors or suppress tumors. They're normal. But the reason they're called that is that if you have a tumor suppressor gene, it's a gene that stops growth. It's a normal gene that stops growth. But when you damage that tumor suppressor gene, it allows growth to accelerate. So essentially what you have is you have a gene that basically hits the accelerator, and you have a gene that hits the brakes. So either you're hitting the accelerator or you're letting off the brakes, or both. And therefore, growth is just going crazy, and that's what's causing all your problems. And then by the late 70s, of course, they discovered these exact genes. So they hypothesized, hey, there must be genes like this. And then they discovered it's super, super exciting. And so they started to develop a few treatments along those lines. So the first couple of treatments were hugely successful. So there's one called imatinib, which is for a very rare disease called CML. And it was a chromosome that got mixed up. And it produced an abnormal kinase, which is an abnormal protein. So that did is they said, okay, now let's go fishing around for a compound that will fix this abnormal protein. And they found it, and it was a pill. And it turned this cancer that was sort of very rare, but very deadly, and it basically cured it. Like the whole thing, the whole disease just basically went away in a couple of years. It was basically nobody had seen anything like this. It was just ridiculously good. Now this was a rare cancer, but it proved the paradigm, and the toxicity was almost zero. Why? Because you're no longer trying to kill cells, right? That's where all your side effects were coming from. You're trying to kill a bunch of cells. Now you're trying to fix the gene product, which is this kinase, so you're not killing cells. So the toxicity was so much lower. It was just an incredible drug. So this is through the 80s, 90s, and sort of 80s and 90s mostly. And then there's this other drug called Herceptin, or is a breast cancer drug, and it was even more brilliant, if anything. So on certain breast cancers, not all breast cancers, they looked for this HER2 new gene. So there's this gene that was abnormal and it was overexpressed. So they developed a product to block it. The problem was that if you gave this very expensive drug to everybody, only a small subset of that population would be expected to benefit. So therefore, it would be very, very difficult because it's just so expensive, and a lot of people aren't going to benefit. So they actually developed the test for this gene, made it available. So now what you could do is you could test the breast cancer, and it sounds, we do this all the time now, but back then it was just mind-blowingly advanced. But you could test for the gene, see if the cancer had that gene, and then give the drug only if it had that gene. So that was the era of personalized medicine. So again, hugely successful product, a huge advance. Toxicity was low because you're only targeting those people that are going to benefit. So it was just a crazy, so this is through the 80s and 90s, there's an incredible optimism.
So you mentioned the two drugs there. And before we move forward, I'm just curious, were these the first two attempts at doing something like this and they happened to just hit grand slams? Or was this further down the road?
This was probably because you're really picking the lowest hanging fruit, right? So you're taking the ones that are falling the most into, like, you're not attempting to cure the difficult cancers. You're just trying to cure one cancer, and then you say, oh, this cancer, which is a relatively, this looks like a good candidate. So it's a low hanging fruit, and that's why it was so successful, because you're picking the easiest one to do, and then you hit the grand slam. But only for that one, right? If you have a different kind of cancer, it's you're sort of out of luck. But on the other hand, for those people that had it, so it's sort of a combination. One, they were grand slams, but it's probably because you took the easiest ones to hit, right? You took the softballs that were lobbed at you rather than, the hard ones. So
Okay, well, let's continue the story beyond that then. So they hit these couple of grand slams with the easiest quote unquote types of cancer to treat that way. What happened when they kept pushing the envelope and getting into the more tricky ones?
yeah, so that was so people were blown away. Like, it was just, people were like, this is incredible. And it really was. So this is through the 90s. People were like, okay, so this is how you're going to cure cancer. We have this new paradigm, which is that the genetic paradigm. It's the genes that are controlling the growth. So whenever you're treating a disease, you got to get back to the root cause of the disease, which is the sort of not the growth, but the genes, because this new paradigm was much more advanced. The idea at the time was that what you're going to do now is simply take one cancer, say colon cancer, you're going to look for the genes and then fix those genes, and then you've cured cancer, right? So you're looking for one or two genetic mutations of each cancer, and then fix it, and then figure out a way to fix it. But hey, that's not that hard. Once you really focus on the problem, then you can find a thing. So this sort of coincided with the sort of Human Genome Project, which was the idea that we could map all the genes of a human being. And this was 2000, sort of finished around 2000. It was very hard to do at the time because it was very expensive. It's all new technology. I mean, nowadays I could sequence your genes for like, $150 in 2 days, right? I could take anybody and sequence their genes for like ridiculously cheap. But this was a multinational sort of thing. It took millions of dollars to do one single person. But that was the 2000s. And they said that this is great. So this is going to basically figure out all the genes of a single human being. We're going to look for these growth genes. We're going to fix them. So it came and went, and as it went on, it turned out that there was very, very few genes for sort of few products that were going to work as well as those first initial sort of grand slams. And they looked for the genetic defects of cancer. And what happened was that as they started to look, by the mid-2000s, they started to realize that there's not just a few mutations in cancer. There's like hundreds of mutations. So if you take a person with colon cancer, for example, it's not the one, gene that's defective or 2 genes that are defective, you would have like 70 genes that are defective, right? Or mutated. So the problem is that it was all different in different people. So if you had one person in your cancer clinic with a type of colon cancer, so person A had 70 distinct genetic mutations. Person B with the exact same looking colon cancer had 70, but totally different than person A. It was ridiculous. So when they cataloged all the mutations of cancer, because they've done this, you're looking at the total number of mutations in cancer somewhere around 7 million. That's probably an underestimate. There's probably like 18 million genetic mutations in cancer. So it's not one mutation, one cancer, right? One cancer, 70 mutations. Well, you can't give 70 drugs to one person and then give 70 drugs to the next person. It's just an impossible task. And that's why the genetic paradigm ultimately sort of floundered a little bit, because it didn't develop the drugs that we needed. So it made very little difference in terms of actual helping, because there's these two initial ones, but even now in 2022, you look at these genetic treatments of cancer and you look at how many of these drugs have actually been developed that have made a huge difference, right? And it's probably about 5, 7 maybe drugs that have really made a big difference, and none that made the sort of earth-shattering impact of the sort of initial 2. So the genetic paradigm was, it is correct, of course, but there was more to it than that, right? Because again, it's not that there weren't genetic mutations. There were. It's just that there was so many genetic mutations. So then, you sort of ran into a wall. And this is where we were in about 2010, 2011. There is, we are 20 years into this genetic paradigm. Every drug company on earth was looking for genetic drugs that follow this genetic paradigm, and nobody could find any because there's just too many. Like, you can't target that number of genetic mutations. It's like, if you're overrun with ants and all you have is like, a bazooka, it's like, well, you can kill one ant with your bazooka, but there's like 10,000 more, right? So you're just getting swarmed by these mutations that you can't treat because you can't design that many drugs. So that was sort of the low point after the genetic mutation, and then realizing that, hey, there has to be something further, because again, what is driving these genetic mutations?
So one scientist started to realize, we're heading down this rabbit hole and we can see that it's not going to have the outcome that we initially envisioned. What was the pivot from there, and when specifically did that happen?
So this is where it gets interesting, and the story takes us to about the early 2010s, I think. And this is the pivot to the evolutionary paradigm of cancer, which most people don't even realize we're in. So the genetic paradigm had clearly failed, but most people, 100% of medical research in cancer was focused on the genetic paradigm, looking for more genes. It's like, you have 6 million of these. Why are you looking for more? Right? It didn't make any sense. But in the sort of early 2010s, the National Cancer Institute started to think, okay, this is going nowhere. So we're going to start to ask other people to weigh in on this cancer problem. So they asked Paul Davies, who is an astrophysicist. And he said to them, what? I know nothing about cancer. And they said, good, because then you can give us some fresh insights into cancer, which is very, very perceptive of them, actually. It was very, very interesting. So anyway, he started to look at cancer, and he started to think about cancer, and he started to say, okay, well, there's a couple of issues here. One, why is cancer doing this, right? So we know that there are genetic mutations that are causing growth. But what is ultimately driving these cells to mutate in this way? The genetic paradigm, of course, said these were random. And that's ridiculous. That's a crazy thought. And it's one of the key reasons why the genetic paradigm fell apart, and it's called the somatic mutation theory. But it says that these are essentially random mutations. Because if you take smoking, for example, smoking is it's a well-known thing that causes lung cancer. But what they're saying is that the smoke mutates genes, but it's not targeted. It's not a targeted therapy. So why is it affecting the growth gene? They're saying what people said was that, well, it's a random mutation. It's just that you're taking so many sort of shots on net that eventually one of them will hit this critical piece. So if you're not taking all those shots on net because you're not smoking, then you're not going to hit the growth gene. Maybe you're unlucky and you get it, but if you're taking, if all this smoke is causing all this damage, which is causing all these mutations, you're taking thousands of shots on net every year, so therefore you're going to affect this one. The problem is that cancer is not random. That is, if you look at one person with lung cancer and a second person with lung cancer, those cancers behave almost identically. They look the same. So how can you say, of the millions of people that develop lung cancer, all of them look the same? You classify them and they're like stage 1, stage 2, stage 3, stage 4, but they all look the same. They all behave the same. They all have the same physiology. If it's truly random, how can that happen? Right? It's like saying to you and me, okay, paint a picture. Paint whatever picture you want. And you and I paint the exact same picture. And then you say, oh, it's just random. And then millions of people with no instructions other than paint a picture, paint the exact same picture. It's not random. It's not random in any sense. You can take a person with colorectal cancer in, 2022 in America, male, white, and you can take a colorectal cancer from 100 years ago on the other side of the earth, a Japanese woman, different sex, different nationality, half a world away, and those two cancers will look the same, even though they have completely different mutations. How does that work? How can you say that's a random occurrence? Right? So that was one of the big problems, is that this idea that this is a random mutation. It doesn't fit. And then he started to think about, why does every cell have cancer? Right? So if cancer is sort of this random mutation, why does every cell in the body, why does it all have the potential to be cancerous? And not just that, but if you look, there's cancers in every animal, right? Dogs get cancer, cats get cancers, rabbits get cancer. In fact, even the most primitive multi-celled organism, which is called a hydra, one of those things in high school where you put a drop of water and you look inside, you see a hydra, very, very primitive. They found cancers even in hydra. So again, this is not a disease of humanity. So if you're looking for the answer of how cancer develops in humans, you're looking at the wrong thing, because it actually goes way past, way, way, way beyond, right? Hydra were there sort of millions of years before we were there. We didn't develop. These are primitive, multi-celled organisms, but they're very primitive, and they still get cancer. So if you're looking at tobacco smoke or something, you may not find it, because you can get cancer anywhere. So that was one of the things I said. So if you're going to look for it, you're going to have to look way back in evolutionary time, because it's not found in sort of the modern human. Yes, it's more common in modern humans because we're bigger, we live longer, that kind of thing. But why cancer develops is not there. And his idea was that it's actually an evolutionary disease. This is a problem that developed as we went from being multi-celled or single-celled organisms to multi-celled organisms. And it's a bit of a complicated story, but that original change from single cells to multiple cells is where cancer sort of originated, because there's a difference in sort of single-celled organisms versus multi-celled organisms. Because if you're a single cell, you're going to want to compete against your other cells, whereas if you're multi-celled organisms, all those have to cooperate. So the single cell has a different sort of priority. It's a survival mandate, right? You got to survive, you got to reproduce, you got to grab resources for yourself, you got to grow, you got to move around to find new environments. And he said, well, hey, that's exactly what cancer is, right? It's behaving like a single celled organism. The whole problem is that this, you know, breast cell, which was part of a multi-celled organism, now has somehow decided that it's going to act like a single-celled organism. It's going to try to sort of grow. It's going to try and grab resources from around it, right? So if you think about it, the breast cancer cell will invade into the liver to grab all its resources. That doesn't happen in a normal cell. The breast cancer cell is going to move around the body, try and spread itself as far as you can. That doesn't happen in a normal breast cell. But these are things that single-celled organisms do. And so the idea of this evolutionary paradigm is that all cells in our body and all cells of multi-celled animals, because we originated from single cells, we have this sort of original blueprint of how to act. And it's a sort of survival, this toolkit, if you will. And this original sort of blueprint never got erased. But as we evolved into multiple celled organisms, what we did was we took this original sort of survival blueprint, these genes that said, hey, grow at all costs, spread yourself around, grab resources from other people, right? This original sort of survivalist toolkit, we never got rid of it. That's not how evolution works. But what we did was we added pieces onto it. We added pieces to say, stop growing, stop moving around, stop trying to, invade other places. So we added all these things to sort of suppress that original sort of intention of the cell to try and compete against its neighbors. And it's sort of like if you take a wild bear and you train it to dance, right? It's still a bear. If you get it mad, it's still going to kill you, but you've suppressed all its natural tendencies. So all the cells in our body have this sort of original blueprint, and that's why every cell behaves like that. So every cell can turn cancerous. In fact, every multiple celled organism can get cancer, and that explains perfectly why that sort of conundrum. It also explains why cancers are not random. That is, if you have every single cell in the body has this original survivalist blueprint, we've added all these extra pieces around it to sort of suppress the original sort of intent. But as you knock off these other pieces, what shines through is this original survivalist blueprint. And it's going to be the same no matter if you're in 2022 or if you're in 1600 BC, right? It's the same original thing. That's why those cancers look the same, because we all had that same original blueprint. Sort of like if we all had the same picture, which is just under wraps, and all we did was we went, hey, and unwrapped it. It's the same picture, right? But it existed there originally. And that's why they look the same, because your picture, my picture, were both there. We just unraveled it or opened it, and there it was, right? As opposed to us painting it, right? Which makes no sense. So that's the idea, is that this original, the way that we evolved, and this is sort of the evolutionary paradigm, the way that we evolved, that kernel of cancer, that original survivalist blueprint exists in every single cell of every single animal that has ever existed. Most of the time, we have all this stuff to keep all that suppressed. Just like if you have a wild bear, you keep it happy and everything's fine, right? You keep it suppressed and it's fine. As you get older, you're going to sustain damage, and the damage is going to knock off one of these pieces that lets it shine through. And things like tobacco smoke, for example, is a source of damage to the cells. So is aging. Aging, you're going to get damage, right? So when you're young, you have all these pieces that keep that original cancer under wraps. Well, over time, it gets knocked off. And then the other thing that's it tells you, so this is the evolutionary paradigm. What it's saying is that the cell is actually evolving to become its sort of more original survivalist blueprint. But that our body we actually have cancer cells all the time. because they're developing all the time, because we knew that we have this sort of original sort of survivalist imprint, right? It's like the wild bear. You know that it's still a wild bear, so you still keep an eye on it. It's not like you just let it go. So our body has actual cells, the immune system, that actually fight this. So if you think about the breast cancer cell as something that evolves into sort of a more, in fact, it's not forward evolution, it's sort of a backwards evolution. So it's called atavism. If what's happening is that you're knocking off all this blueprints, you're allowing the original sort of playbook to sort of emerge, well, that's happening all the time. So therefore, our body has developed defenses against it, and those are the immune system. So when you develop this sort of original, you've actually turned almost into a new species, and that's how our body sees it. It's like a new invasive species that it has to fight. So anything, and this is happening all the time. It's happening in you, it's happening in me, it's happening in everybody. But your own immune system is going to find these sort of people and target it, just like, a policeman, right? It's like you have a city and you have policemen, because if you have criminals, you go and catch them, right? Same thing here. As soon as you start to see this new species developing, that's sort of the original sort of single cell, instead of, it's behaving like a single cell, your body is like, oh, okay, we need to get rid of it because it's going to be a problem. So it sends it in and gets rid of it. And then it's really as if you stress the system. So if you suppress the immune system, you're going to get cancer. So every single drug that suppresses the immune system raises the risk of cancer. But anything that's causing damage to cells, right? You have this original cancer playbook, you have all this stuff here. Anything that causes chronic damage to cells is going to cause this damage and allow this sort of kernel of cancer to shine through. So whether it's tobacco smoke, which is chronic inflammatory damage, or it could be radiation, chronic low-level radiation can do it, like we used to see in in the radium, the exposure to radiation early, before we realized it caused cancer. Asbestos, for example, caused chronic inflammation. Any chronic inflammatory disease like hepatitis B, hepatitis C, they would cause cancer. Anything that causes the immune system. So this evolutionary paradigm says that, hey, the problem is this: we have cells that were originally going to behave like single-celled organisms. In evolutionary time, we've created things to suppress that, and as you knock off the things that are suppressing it, it's allowed to go through. So they've actually looked now at the study of the genes that cause cancer. And what's very interesting is, instead of just saying, oh, what are the genes? They went back and they said, let's look at these genes that are mutated during cancer, and let's look at the evolutionary age of them. And all of them are concentrated just at that transition from single cell to multiple celled organisms. It's very, very striking. So all of those mutations are there. All of the more recent genes that we have, it doesn't matter if you mutate them or not. It makes no difference. It's those genes that are sort of suppressing that original single cell tendency. All the more recent genes, you mutate them, it doesn't matter. But you mutate those genes that are taking care of that problem, then you do get cancer. So the idea is that it's really a reaction to a chronic damage. Any kind of chronic damage can cause cancer. And if you think back as to what causes cancer, because people think, oh, we don't know what causes cancer. No, we know a lot about what causes cancer. Smoking causes cancer. Asbestos causes cancer. Soot causes cancer. All kinds of things cause cancer. But all of them cause chronic damage to our bodies. And that's again, it's not saying that the genetic paradigm was wrong, but it's trying to go that next step and say, why are all these genes mutating, right? Just like the genetic paradigm said, why are all these cells growing? Well, it's because of genes. And it's like, why are all these genes mutating? Well, it's like they're evolving as a reaction to chronic cell damage. So therefore, they're sort of going backwards in evolution towards a single cell.
What you're saying there is the paradigms before make sense. They just aren't sophisticated enough to have all the nuances like you just explained, which is fascinating. And knowing now what you just explained, it makes a lot of sense. But of course, it's only because we're, looking backwards now. I can see why it took a while to get there.
Yeah, exactly. It's not that people were stupid or anything. It's just you're basically going one level deeper into why, right? So you've got, hey, cells are growing. Then you say, why are cells growing? Then you say genetic mutations. Then you have to say, why are genes mutating? It's an evolutionary process against chronic inflammatory damage. So therefore, that's where it is. And now, you're not going to stop a lot of these things in terms of chronic inflammation. So ulcerative colitis or something, like, yeah, you'd love to get rid of ulcerative colitis, or if you can identify it like tobacco smoke, then you can get rid of it, or asbestos, then you can get rid of it, right? But the other thing that's important is that certain things, now you say, okay, cancer is not a genetic problem. It's a problem that they've evolved or sort of gone backwards in evolution to these more primitive, right? So it's not a forward evolution, it's a backward evolution into a more primitive form. What's interesting, of course, is that that's the way pathologists have been describing cancer for 100 years. If you look at the pathological descriptions of cancer cells, they're called primitive, right? Anaplasia, which means going backwards in time, right? All of these terms tell you that they're not getting more sophisticated cells. They're going into a more primitive state, a survivalist state, a single-celled state, right? So that's exactly the way we've described them. But then now you have to try and figure out ways to deal with them, right? And that's the sort of challenge of the next sort of like 20 years. But that's where we are. And it's a really interesting story because, again, a lot of people just think it's all about genetics, but it's actually a lot more complicated than that. So, for example, if you have growth factors, well, growth factors are going to promote growth. So one of the things, for example, is obesity. If you have an excess of insulin, insulin is a growth factor. So therefore, that's going to play a role in cancer. And that's exactly what we found. So since the mid 2000s, say, what we've started to realize is that obesity is actually a huge risk factor for certain types of cancer. In fact, the World Health Organization identifies 13 different types of cancer as obesity-associated cancers. So again, that's, obesity doesn't cause genetic disease. It doesn't cause gene mutations, right? You've moved already way past the genetic paradigm. Because if you're calling this an obesity-associated disease, in the past, you'd have to say, so how does obesity cause gene mutations? And the answer is that it doesn't. Obviously not, right? But what it does is it is an excess of growth factors like insulin that are going to help the growth of these cancers that are developing. Since cancers are developing in all of us, we police them. But so there's always cancers developing, but we have very, very strong anti-cancer forces. So there's always criminals, but there's policemen. That's essentially it, right? So usually the policemen are like this, and it just squashes the criminals. That's the same thing. So normally we have cancer, but we have lots of strong anti-cancer forces, and they just squash them. If you give immune suppressants like prednisone or suppress the immune system for any of these autoimmune diseases, what happens is it goes like this, and then the cancers are okay. With age, same thing. Everything goes down with age. So immune system goes down with age, which allows the criminals to do this. So the other thing is, of course, that if you have obesity, you're going to have growth factors that's going to help the growth of these things, right? So it's all a balance between sort of the cancer, which is there in everybody, right? That's a totally different thinking. It's present in all of our cells. It's actually this balance between pro-cancer and anti-cancer. Normally anti-cancer is like this, right? So that's where we think. So then we say, okay, well, immune system is there to sort of squash this, right? So what can we do? Well, that's the whole idea of immune therapy now. That's the sort of next big wave. It's already here, of course, if you look at the way that we treat cancer. It's a big thing. So one of the ways is that, okay, again, you think about criminals and policemen. Well, these criminals were hiding. That's why they were able to survive, right? Because the policemen couldn't find them. And one of the ways that the immune system, that the new immune drugs, is to open up and expose them so that the policemen could find them. So that's exactly how some of these immune therapies work. They sort of break apart the sort of cloaking shield that these cancers had, and all of a sudden the immune system can see them, and it goes in and squashes the cancer before it gets to be a problem. But again, it's a totally different paradigm now. What we're trying to do is we're not trying to fix genetic problems, right? So cancer paradigm one, growth paradigm is kill. Cells are growing, kill them. Genetic paradigm is cells are mutating, let's find genetic cures. Now we're like into this sort of evolutionary paradigm, which is like, well, cancers are like an invasive species. Let's kill them with our immune system. Let's boost our immune system. Let's figure out ways that we can weaken them, right? A totally different way of thinking and a totally different paradigm that most people haven't recognized that we're in. Even oncologists, like even a lot of cancer specialists, they spend so much time thinking about treatments that they don't think about the sort of very interesting backstory of what is cancer, right? What is this thing? It's more like an invasive species than it is a genetic mutation problem. It doesn't change therapy so much, but it's an interesting way of thinking. So it shows you that there's multiple ways of attacking it. So whether it's immune therapy or boosting the immune system or trying to get rid of these growth factors like obesity.
If you enjoyed that clip, press here for the full episode. I'll see you over there.
These studies have been replicated over and over and over for the last 30 years of attributable risk. And diet and obesity is that second huge bucket, and nobody's talking about it.